Hi everyone, welcome to Reason with Science. I'm your host Jitendra. This episode is with Lee Cronin. He is the Regius Chair of Chemistry at the University of Glasgow. He and his team are trying to make artificial life forms, find alien life, explore the digitization of chemistry, understand how information can be encoded into chemicals, and construct chemical computers. In this conversation, we talk about topics related to origin of life, framework to build life from inorganic material, assembly theory, Darwinian evolution, and alien life. Enjoy the conversation, share and subscribe to support the podcast. Thank you for listening. Yeah. Hi, Lee. Welcome to the podcast.
Nice to be here.
So how do you, or let's start with that big picture view, like how do you study the origin of life? I mean, there are, of course, different point of views that people use or in science that we are exploring nowadays. So what's your point of view or how do you look at this origin of life research?
Yeah, there are many points of view. I prefer to be the most fundamental I can, which is to say, life on Earth right now, autonomous life on Earth, is based upon cells. And so we need to work out how to make autonomous objects like cells. So we literally need to work out how chemistry gets transformed into biochemistry as presented by a cell. I like to look at origin of life from the fundamentals, which is what is life? The minimum unit of life we know is a cell. Okay, it could be that viruses also are a similar form of life, but actually cells autonomous and can turn over. So really, I think the most important thing for us to do is to actually try and build objects, machines, entities, if you like, that are able to act like cells. That's produce complex molecules, produce genetically applicable polymers, proteins, like materials, catalysts, things like that. So we really need to be able to engineer life from the bottom up to understand it. And so my perspective is really fundamental from that point of view. It's not about just making molecules that you find associated with biology in plausible ways. It is about making a biology.
Yeah, but then there are, of course, different scales of it, right? Like we can think of people that they are working on prebiotic chemistry, for example, or a biochemist like me that they are trying to just put together the biomolecules and try to create cells. So what's like how?
Yep. No, I think they're the same thing. I mean, it's a bit like saying, how do we explore gravity? You can use a big mass or a small mass. People that are working on prebiotic chemistry, and we do that as well to some degree, prebiotic chemistry is prebiotic. People working on biology are postbiotic. What we really need to understand is the transformation from prebiotic into biotic. There is no other question. We can dance around it and pretend it's other things, but it's not. The transition to life is that. We need to go from prebiotic to biotic chemistry. I'm not saying that no one else is doing it. I just think that lots of people are treating it like a history lesson. It's not. Life is not. Life didn't just occur in the past. Life is here now, and life is probably emerging elsewhere in the universe. Until we start to even open our minds to that, I think that we are missing a big part of reality.
Exactly. That's quite interesting. And especially that means we need to understand those underlying principles of life so that we can, even if we are exploring it somewhere else in the universe, we can kind of detect it in a way. So what's your like fundamental framework that you are working on to build life?
I mean, I suppose the simplest way to put it is I want to turn sand into cells. Okay, I mean, that's the simplest way of phraseology, putting it. So what do I mean? So sand is a kind of a catch-all term for inorganic, non-biological stuff, simple stuff. And I want to see how over time in the environment, so they're really important things. So how an inorganic thing or ensemble things over time in an environment becomes biological. And my approach is exactly that. So what I've tried to do is break it into kind of 4 components. And that is a fundamental theory for what life is, which I think is totally unknown. we've got some hints, a model that takes that theory and produces a abstraction of what life does, then a test for that comes out of that model, and then a machine to make it. So theory, model, test, machine. That's the way to do science. So the problem we have right now is that there is no theory for life, so I'm having to build that. There's no model for life, because I'm having to build that. There's no test for life, I'm having to build that. And there's no machine built just to make life, having to build that. So we're having to do all four components. And of course, there are lots of other people working, but they are working at the periphery. Like, in prebiotic chemistry, well, maybe I'll try and look for RNA, or maybe I'll make a mess, or maybe I'll make a lipid, or maybe I'll put in some amino acids. All that's great, but I think that's missing the target with regards to what life is, what is the model, what is the test, and how do we make it? Because if the origin of life is a untestable, unfalsifiable phenomena, then, and some people argue that it could be, until we've actually done it, it's quite hard to think about that philosophically. But we can, and just from probably your point of view as a biochemist, protein biochemist, you can do engineering and biology, which is interesting. So you can find out how biology works, what it is about a cell. In prebiotic chemistry, you can work out how to start making interesting molecules which are found in cells. So there is some connection there, but I think it's a very long road for those. So I prefer theory, model, test, experimental test, build a machine to do it.
But let's kind of go into these components. So what's the theory here? So the progress that you've made so far with assembly theory. Let's talk about that.
It's not just assembly theory, it's just the notion, but assembly theory does describe it. So assembly theory is just a theory that seems to explain, or attempts to give some explanation to and prediction to, the fact that the universe is able to produce complex objects, right? And what I mean is only those parts of the universe which have undergone evolution and produced technology. So what is the theory? So let me try and put the theory away from assembly theory. So my theory of life, or the theory of life that I think we're coming to, is that that the process of selection, which occurs in the universe without life, abiotically, in the presence of any heterogeneity, any presence of molecules and materials, very basic molecules and materials can act as both the environment and the objects being selected on. So they kind of interact together at different timescales. And then objects that can exist over a very long period of time and not be dissipated are interesting, especially if they can act to help make copies of themselves in some way. So it's that, if you can imagine it, if you imagine you're making an infinite number of objects, but they only have a finite lifetime, they will all cease to exist after some time. If, however, out of those infinite number of objects, there's a small subset that can either make themselves or act on the chain of events that made them to amplify them being made, over time, as all the other objects die, the only objects that will exist will be these objects, these complex objects that can either act on the past history, if you like, the causal chain, or copy themselves to make themselves. So for me, life is a natural phenomena that emerges from the need to exist. And this is what we see in biology, in Darwinian evolution, survival of the fittest. So I think the survival of the fittest, that my theory of life is that survival of the fittest was occurring even before biology, okay? And it just took a very long time. And for those objects to continue to exist in time, they needed to become more and more autonomous, because in the end, the environment would just get them. They would just be dissipated, burned, destroyed, dissipated. So I think that's a really important point I'm trying to get to grips with. So I think I'm saying that life is two things. It is the ability to build memories, heterogeneity, record what's happened in the past, and the ability to propagate those memories through time and space into the future, such that they are productive. So that's the theory. Then the model, if you like, of that is kind of building, making like almost like a theoretical model where you could generate objects colliding with one another, building more complex objects. Maybe you could have like a toy model that would do this. And then assembly theory bridges the theory of life and the model by saying, how can I actually measure the emergence of complex objects over time? And how can I do it in such a way that I'm not being fooled? And so what assembly theory says is, well, hey, first of all, I need to find objects that are identical with respect to my measurement device. And I need to find objects that have a large number of independent parts. Because the larger the number of independent parts, the larger the memory. Larger the memory, if you find that object in lots of copies, the lower the chance it just spontaneously emerged in the universe. In fact, the chance that a complex object in many copies just spring into existence in the universe is basically zero, effectively zero, because it's so contingent. And so so that's kind of where we're going. And that's kind of the assembly theory, like, is the test that bridges the fundamentals of what life is, selection of existence. So people think, what is life? It's just selection of existence, or select to survive. Biology just supercharges it. Biology is able to massively take in a resource and copy themselves, and planet Earth is very successful. There's lots of human beings on Earth, lots of cells, lots of insects, lots of biological creatures, and they are selected to survive.
Yeah, so, but for Darwinian evolution, we draw a line at the life forms, or people go back, let's say, till Luca or something, right? But then where do you draw the line if we go beyond that?
So I think that's a very interesting question. I think in Darwinian evolution, if we define evolution as the needing a genetic machinery that undergoes some kind of mutation, and that mutation process is the mechanism by which you get fitter and fitter phenotypes. Okay. The thing about looking at the transition to life is that there is no life-death transition. It's just suddenly you find yourself to the point where the stuff is more autonomous, right? In a way, life is not, even if you define life as autonomous replication, even on Earth, there's nothing autonomously replicated. It's all bound to Earth. We won't survive in space for very long, or Mars or the Moon. We have to be tethered to Earth. So life really is a phenomenon which is tied probably to some kind of planetary scale, although some people would argue with that and say we could have life off Earth, but at the moment it would appear that some emergent effects, or not emergent effects, some feature of a planetary scale, and it's gradual. And so there's pre-Luca life and there's post-Luca life. What is post-Luca life? The technology we all love and know in biology: ribosome, RNA, DNA, proteins, our metabolome. Before Luca, there are probably many other chemistries almost alive, doing very similar things, but Luca was the one that got selected because it was the best compromise for the cost of selection and existence. There might have been ones that are much better at selection, but they didn't exist for quite long enough. There might be ones that existed for a longer time but weren't selected enough. Luca seems to have been a compromise on those features.
Yeah, and what about then the selection post Luca?
Post Luca, well, so yeah, I'm not sure if I answered the question going back pre-Luca. So pre-Luca selection is not genomic. It's basically heterogeneity and very happenstance. Then you get to Luca, and you've got the ribosome and the DNA and proteins and all this interaction by RNA. And then as you go further up, you start to have intelligence emerging, consciousness, and the ability to abstract. And then that seems to be another layer in evolution, because we can start to build objects that are not tethered to our evolutionary history. Whether it's something like this pencil, which on the the surface of it looks very simple, but it has a graphite center, it has this wooden outside, it has this metal part here, this tin part here, and this rubber. So all these components, I don't know if there's any one person on the earth, I think it's been said, that couldn't make a pencil with all of this sophistication. It seems really obvious that it should be easy. It's got nice kind of red writing on it as well. So you've got, there's a lot contained. And so post-Luca, we start to get culture and memes and technology. And I think that, when people worry about super intelligent AI, they're wondering about the wrong thing. There's not a super intelligent AI. It's just going to be humans with mathematical tools that can do things that other humans couldn't do.
Yeah, it's more like science fiction-y stuff rather than reality, at least so far, right? Mm-hmm. And of course, we'll get into the details, like the difficulties that you faced while developing Chemputer, for example. But before that, so in terms of theory, so even if, let's say that we say that matter has some sort of property and the selection is going on, mm-hmm. But for example, how do you look at, but even in that scale, we can go at the, atomic level or even subparticle level, etc., right? So what do you mean by memory? What do you mean by memory of those atoms, for example? Many of the physicists, they say that all the electrons, they appear the same. So, so what does that mean? Like, where is the then boundary,
Physicists like to mix abstractions of reality with reality, don't they? The fact of the matter is I'm a materialist. And although I can produce electrons with an electron gun, I have a model in my head of what electrons are. That doesn't mean they are. When the model becomes the thing, you start to get into very sticky ground. So we should be really careful about that. So physicists have in their model things called electrons, consistent with the observed experimental and theoretical data, and they seem pretty good. But I just, but let me ask the question directly. In physics, you've only got a limited number of conserved quantities, right? In charge and mass, momentum, and so on. Energy rather. And when you talk about subatomic particles, there's a finite way you can organize them. And if you organize your quarks and you get your nucleons, and your nucleons with electrons give you elements, there's only a finite number of things you can do with quarks. Okay, and then there's only a finite number of things you can do with those fundamental particles. As soon as you get atoms, that is an element with a given atomic number, so a given number of protons and number of electrons, that takes its own particular chemistry. So different number of protons, different chemistry. And obviously all high school students know that chemistry, different neutrons, different isotopes, same chemistry, pretty much. Not identical because there are kinetic isotope effects, but pretty much. So when you have electrons bound to an atom and there are layers, there are a number of ways you can reorganize those electrons to form bonds. So you can bring different nucleons together, if you like, right? And so what you can do by making these bonds, and these bonds have an energy, there is some conserved structure for a compound. So let's take water, H2O, really simple. One oxygen atom, two hydrogen atoms. In this case, the hydrogen would have one proton and one electron, no neutrons, okay? Whereas with deuterium, it would have one proton, one neutron, and so on. And so you've got this molecule, water, 3 atoms and 2 bonds. Now, the ability to take carbon, which can bond to up to 4 different elements, or phosphorus that can make up to 6 different bonds, you can start to have a combinatorial explosion of possibilities. And when the explosion of possibilities is so big, then you start to get a very interesting set of things happening because then selection can start to occur. And so that means selection can drive you to many, many outcomes. Whereas if you take a given set of, quarks together in a plasma, kind of quark gluon plasma, you're going to produce relatively, a very not just combinatorially simple, but relatively simple mixture of materials, and might even converge, right? Just might end up producing hydrogen or something. So I think that the most important thing is that life emerges at the scale at which you can start to do selection. I wouldn't say selection is occurring when the combinatorial space is small. That's just more of a solution to a simple problem. Now, it may be a war on words, and it doesn't matter, they can say selection all the way down. But what I mean is that in physics, you don't really see selection because there's not enough combinatorial processes. In chemistry, you see a huge amount of combinatorial explosions. In biology, all you see is selection.
Okay, so this is interesting. So let's say that with the formation of a star, chemistry starts, because before that it's mainly hydrogen in the universe, right? Mm-hmm. And once the chemistry is there, then of course with the use of energy there is more complex chemistry, and then there are these different possibilities, or a huge chemical space, as we would say, right? And on this chemical space there is a selection. And this selection is based on the stability of that compound in
I mean, there has to be some stability, and I think that's because if it's too unstable, the timescale for selection won't occur, and so you have a real problem. So I think that's critical. If things are too unstable and selection can't occur, then there is no memory to be made. If there is some stability that can direct the outcome, then obviously selection can occur.
And the memory is the path taken to form that compound or chemical?
Yeah. It's encapsulated in the compound. I suppose the memory exists in the causal chain to make that compound. The existence of that compound, or my pen, my pencil, or whatever else, is just proof there was a memory.
It's basically both the conditions and the path taken to form the compound. Yeah. So because this now nicely explains the emergence of the different chemicals that we see around. But then how do you fit assembly theory here, or what do you do with the assembly theory to explain emergence of life?
Well, assembly theory does not yet explain the emergence of life. I think that's critical to explain. We're working on it. What assembly theory does is it allows you to do two independent things. It allows you to detect life, and it allows you to explain why physics turns into chemistry, then biology, by storing memories, or to identify processes that are giving that are contingent. And assembly theory in that regard is really a way of it's almost anti-entropy, where entropy tells you about the amount of disorder you have generated. Assembly tells you about the amount of contingency that has been created or required to do a certain thing. And what we're trying to then use that to do by using assembly theory to identify where causation has had an effect, and then look at the mechanism, microscopic mechanism, and go, oh, origin of life is this autocatalytic set coupled with existence, coupled with this type of chemistry. I mean, I think we're going to find what causes life in the end to be relatively mundane and not magical. And a bit like, gravity is like pretty mundane. It's like, although it's still magical because we're still arguing about whether we should unify gravity and quantum mechanics, which is kind of, not sure that that's actually the correct question, because gravity is a complete theory and quantum mechanics is really a probabilistic process, a series of mathematical tools for using probabilistic analysis to understand some physical processes. And people keep getting confused, thinking that quantum mechanics is actually something deep and meaningful. It clearly isn't right now. That's what we keep getting stuck.
Yeah, all the scientists working on multiverse won't be happy with this statement, at least. I
don't think so. Think about the multiverse for a second. the whole idea, the Everettian interpretation of quantum mechanics, if there is to be an interpretation, seems to be correct. But the physical interpretation is clearly incorrect. The universe is not branching. And this is just, I think David Deutsch explains this extremely well, in that we're trying to explain a narrative in quantum mechanics which is not appropriate, because this literal interpretation of the wave function collapse is not what was, it's not physical, right? And when something isn't physical, to try and make it physical, to have this multiverse, it's kind of insane. It's like, it's a bit like people say, well, I'm going to go faster than light, and I'm going to break causality. I'm like, well, you can break causality by going faster than light if you want, but it's not physical, and we don't see any evidence for it. And science is about coming up with explanations that are that help us understand the universe.
And also some sort of empirical way to show it, because I don't know if there is any possible way to show the universe is branching off, right?
Well, I mean, it doesn't make any sense. There's not enough mass in the universe to do that, right? It's like, it's not, what the Everettian approach is saying is that if you take the deterministic nature of the Schrödinger equation, is to say that the universe tends to be in the branch that's most populated, right? And it might explore other paths before it kind of goes into the future. What the Everettian view is kind of really saying, well, we don't really understand we don't really understand time. When you say that, then all the things are going to go crazy. How there's only so many arguments I can have at once, whether with a biochemist, the origin of life, a physicist, and so on. Arguments aside, we should all be unified by the question: what is the nature of reality? What is life? And I'm kind of trying to ask that at the borderline between physics and chemistry to understand biology. And the simple fact is, our current understanding of physics is not able to produce biology. And that's all I'm finding fascinating, right? That physics can allow us to do such wonderful things in electronics, communications, power generation. We might even be able to get fusion sometime soon. Yet we do not understand what life is and how to make one. At the most fundamental level, we have simply no clue.
Yeah, I mean, when I talk to my colleagues and friends, this is what I mentioned, that if we look how much, even at biochemistry level, we know already about a simple cell. It's unbelievable that we can't just put this stuff together and get kind of autonomous system, of course, with the conditions.
Oh, I think it's totally believable. Let me give you an example. Let's say you have a really old motor car, or you have a really new motor car and a really old motor car, and the really old motor car is 70 years old. That'd be an old motor car, right? And that motor car has, it's done millions of miles around the world, and it's got all these scratches on it and everything else. And when you try to make let's say right, you now need to make, and let's say this motor car, you're really lucky, not only is it 70 years old, it's done 70 million miles, so it did 1 million miles a year for every year of its life. You didn't really need to change too many parts, right? And most of the car is there. And then someone says, okay, I want you to make a copy of this motor car, precise copy, an identical copy. There's no way you can do that. You can make a gross copy by just looking at the blueprints and facsimiling it, maybe putting a scanner, 3D printing stuff. But all the indentations in the ball bearings, the rust on the exhaust pipe, the pits in the piston, the plastic fallen, the rubber, the leather that had fallen off the steering wheel, and the stitching that had come away, and all this stuff. The only way you could produce that really is to go back in time to where the motor car was and go through exactly the same lifetime. Someone bashing it at the same time, scratching it, leaving it outside of the rain, whatever else. If it didn't have a cover on it, it was an open, car. So what people misunderstand when they see a cell, this is really powerful. A cell is not just something that instantaneously exists now. It has a 4 billion year depth in time. Just in the way that motor car had a 70-year depth in time. But all the features of that object are accrued in time, then you can really understand exactly how featured the cell is if the cell is just an object in time. Now it's an object that can create other objects via replication, and that orchestration is embedded in that causal chain. And that doesn't mean to say at some point we won't know how to make a fully autonomous cell from scratch, but right now we don't. And it's not because creationism is correct and God did it. It is because we do not understand the most contingent parameters, or what we don't understand the most important things that happen to that cell to put all the right metabolites, mechanism, machinery, catalysts, whatnot, in that cell ready for it to turn over. And I think that the complexity of the cell, when you view it from the lens of this object has accrued features over many millennia, it then becomes entirely understandable because evolution has become happening all the way back to Luca, and probably before. In fact, the evolution before Luca was probably even more radical than post-Luca.
And how would automation will help in this thing? Because we can think of 4 billion years, but we can't spend 4 billion years to kind of evolve a life in the lab, right? So we need to do it fast. And
you can turn time into space. So what you could do is you could say, if you did something, if you imagine everything coming in a flow system and you had a long enough pipe, and let's say it took 1 day for the material to go this second down the pipe, and you had enough for 365. So you could probably start that process going, obviously wait years going down the pipe. But then when you actually do your experiment, you've got an entire year of evolution happening in that pipe. So you can turn time into space. But you can also multiplex. You can already divide up the reaction into many different components and mix them together. And you can add on, you can add in complexity by hand or by algorithm, and just acknowledge the fact that you put in that information. And so when you make your life form, you have to acknowledge that you are the god of them or the creator of that life form, right? It's a joke. There's a bit of a joke, but joking aside, if we were to make life, when we are able to make life in the lab and we have to do the experiment, to some degree, we set that up.
And what would be the information from your point of view?
From the lab, reagent concentrations, the fact we're putting in pure stuff, the apparatus, the fact the apparatus is pure, the digital control, all these things counts up with, not quite cheating, but these are external controls that we have to account for. You could imagine an early Earth with maybe some liquid, solid, gas interface, right? Liquid, the sea hitting the beach, hitting the atmosphere. And that might be, enough to start thinking about how you can start to generate programmable processes. Why? Because the tide goes out when there's a moon, right? Or, so you can have the tide in and out. That's equivalent to an oscillation. That oscillation you could do automation, or you could do near a beach. It's just you can speed it up by doing automation because you don't have to wait, how many hours it is for the high tide or a low tide. Whereas in the lab, you can just, oscillate very quickly through the reaction mixtures.
So in a couple of days, I'll be talking to Mike Russell, who has kind of highlighted the importance of environment and the conditions which were there at the origin of life. And he also gave the idea of hydrothermal vents, etc. So, or the origin of life at the hydrothermal vents. So and if the conditions are important, then how do we figure that out? Or it's again up to us, like we try again different set of conditions and we see which one works better.
I don't think the conditions are that important, except for, so if you think about it, it's like the problem with the origin of life, people, including Mike Russell and prebiotic chemists in general, it's not so much a problem, it's more what they're doing. They've chosen to try to fixate on a particular event they imagine can happen on planet Earth. It's a bit like us fixating on our sun in our solar system. So how did that star form? I want to know exactly how that star formed. Where did the gas come from? Was there any other material? What time did it ignite? How many seconds have been going? What's the future? Or you can do that with just one sun. Or you can take a more statistical approach and say, look at all the suns in the universe. Some are living today, some are being born, some are dying, and have a look at the common characteristics. And I think it would be great to look at life statistically and not just fixate on one set of parameters. Of course, hydrothermal vents, do they provide some of the engine for complexification? Sure, could be. Could they be the most important? Important with respect to what? Do I care? Not really. I just need some energy and a flux, right? I'm really interested why people are trying to obsess about the exact device. We're going to make a fusion engine sometime in the world in the next 20 years, right? Are we going to care about how we did that precisely with respect to star formation? Star formation is a load of gravity clumping up, so a load of hydrogen clumping up, getting to the point where you cooper up more and more hydrogen. And if you're lucky enough to be pure hydrogen, at some point it will self-ignite and you'll get fusion. Are we any different?
But then what's the sort of that essence of life? What do you think that can just make it happen? Is it simply the self-organization?
I wouldn't. Self-organization is a funny word. I would say that the reason why life happens is that you need varied chemistry, and you need some time, and you need varied phases. The moon is lifeless, and likely always been lifeless. Its lithosphere is just very, very limited. Mars might have been alive or temporarily doing something interesting. Same with Venus. But is Jupiter had life on it? I doubt it, because it's so high pressure and it's probably pretty hot. So I don't know. We just have to think about it super carefully about what is testable and what is frameable, and that will get us a long way.
Yeah, but do we then need to kind of understand since you just mentioned about Jupiter and high pressure, at least do we need to understand what sort of conditions are important, or like at least in the Earth's case, what is important? So for example, whether do we need to use oxygen or
no, I think this is what conditions are important for gravity? Mass. What conditions are important for life? Heterogeneity. That's it. It's not complicated, I think. And there are people like to really just make a more and more complex narrative, and it's just not testable. And as soon as the narrative becomes untestable, it's just a narrative. It's just a story. We may want to say hydrothermal vents are the origin of life. I bet they're not. I bet they're one source of the origin of life. Or wouldn't it be interesting if origin of life stories, there'd be hydrothermal vents and other aspects that all play together to give you this chance event that was one in a gazillion. Or have enough mass, you make a star. Have enough events, you make a life form. Because if you have enough events and some stuff, if the stuff can persist for long enough in time and also make itself or influence the process that made it, it's going to be functionally alive. And it's so obvious. It's like really breaks people's brains.
Yeah, but then it's also this question, right, or this observation that out of 8 solar planets or planets in our solar system, we have life on only one, at least so far, or the kind of proof that we have.
At this time, and what does that mean? What we're saying is, if we're saying that life is about heterogeneity, the most interesting chemistry anywhere in the solar system seems to be on Earth. Although Venus looks pretty cool, well, not pretty cool, it's pretty warm, but there's some interesting, maybe some interesting chemistry in the clouds of Venus. Mars needs investigation right down under the surface. The moon looks pretty boring. But the rest is like wide open.
Yeah. And so let's say then how from your theory you will reach to some sort of a living system, let's say so it'll be, as you said, that just using some pure components, forming these different components and mixing them together, or at the end, like what exactly do you need there?
What is the experiment, you mean?
Yeah.
Well, if I knew the experiment, I would have done it already. I think along the lines of mixing stuff up randomly and looking for complexity, and to keep going until the complexity goes through several jumps, and then zoom in and look at what happened mechanistically. I think that's probably super important.
And because we need some sort of platform in a way to embed some sort of information. I mean, of course, in the present life forms, we have DNA. There is then this RNA world hypothesis and stuff like that. So are you, or do you think that you'll go along the same lines, or it can be something else?
It can be definitely something else. I love to wind up the RNA fetishists. All right. I mean, it's like people say, well, RNA is quite good at catalysis. It's like, no, not really. Okay. I mean, chemicals can do, any material can be catalyst for something. Say, oh, there's evidence for this, that, and the other. Until you actually put a load of RNA in a cell and make it alive again, you just don't know.
Let's talk a little bit about Chemputer and the kind of challenges that you've had building it. Now I think you have it already running, right? Like you are already working with it.
Many versions, many different types, yeah. So the Chemputer was kind of the result of me wanting to build a massively parallel origin of life experiment, and thinking, wouldn't it be great if computer control everything, the addition of solids, liquids, gases, that looking for complexity coming out and all this stuff. And so what I needed to do was to build a hardware infrastructure, an operating system, a software infrastructure, and then basically a way of programming the robot and doing kind of cluster, experiments, whatever it is we're making. Inorganic clusters is one of the things we're looking at, kind of producing in these computers, organic molecules, materials. And so there's the origin of life, kind of material, inorganic stuff. Can we just program it all? And then there was like the realization you have to make this programming language for chemistry. And so what I hoped I could just build this robot to make an origin of life machine. But even the infrastructure didn't exist. It was like someone saying, "Oh, I'm gonna build an app to, I don't know, do shopping or something, or give music out." And then it was like, but there's no digital infrastructure, and there's no hardware either, and there's no standard. And by the way, everyone's just going to fight about it because everyone thinks it should be done manually. So when I started about 10 years ago, we had all the chemists saying, "No, this digitization stuff ain't going to work. This machine learning stuff ain't going to work. And by the way, we're really important." And I was like, okay. So I started to gently design the infrastructure. So I started with the hardware rather than the software. I had the software kind of built, the abstraction built of chemistry. And then I started to kind of realize that, okay, I could make inorganic clusters and minerals and stuff, origin of life experiments. I could squirt things together and all this. But actually, wouldn't it be really great if I could just do like really hard organic chemistry that people wouldn't necessarily want to do on their own, and start digitizing that? And that's what we started doing. In about 3 or 4 years, we built the first prototype. And the first prototype was able to make a range of different drugs, 3 different drugs, 8 different reactions, all the same hardware. No change in the hardware, just changing the chemicals and changing the digital code. And once we made the first Chemputer, we then realized we could, the programming language we constructed could work, so put the programming language on there. And then we decided to say, oh, now we can start to take well-known molecules, take the code that's used to make them in the literature, turn it into KDL, computer code, and run it on the robot and make the molecule without any manual interaction or minimal manual interaction. And that's what we've been doing, and it works.
Yeah, it's fascinating. I recently had a conversation with Michael Levin, and he was talking something similar, that he's like, we should be able to kind of 3D print whatever life form that we want, like just to kind of draw it, and whatever head shape and this kind of stuff, whatever we want, we can kind of just 3D print it and have it as.
But do you think that's possible?
He's trying. I don't know if you've checked his work or.
Yeah. I mean, I can tell you why it's. Remember the story of the car I told you, the 70-year-old car.
Yeah.
Why couldn't you copy the car? Same reason why you can't copy the cell. Now, I'm not saying it's not possible to engineer tissues, but right now we don't really understand how that works. If you really want to 3D print a biology sample, you have to put it through evolution. And you can't just 3D print stuff. It doesn't work. You lose contingency. So until we understand how that contingency is built in, it's going to be hard. That doesn't mean it can't be done, but I think people are so far away from even understanding that people are just deluded by the ease of software engineering and digital representations. And they go, oh yeah, we can just 3D print that, I'll copy that, do that. Really? It's like the Boltzmann brain fantasy. You know what Boltzmann brain is?
No.
So the Boltzmann brain is this idea that in a vacuum, suddenly an object could just spring into existence. That's a human brain that's fully conscious in somewhere in space. That's a complete nonsense, because the human brain isn't just one object it can copy. It required 4 billion years of trial and error over an entire planet to make. Your brain, my brain, everyone's planet isn't just your brain. It came from 4 billion years over the entire surface of the planet to be created, going all the way back to Luca. Until we understand that chain of events, we ain't going to replicate it. We might get somewhere. We've taken analogies from the brain, we made neural networks and so on. But 3D printing organisms without understanding evolutionary embodiment, I think that's going to be super tricky, because a lot of the memory that you have in the organ, in the object, comes from that evolutionary history. Not all, in fact, the genome doesn't encode that much. It encodes just enough to recreate the trajectory that has been evolved upon. And that is also something that people think is probably heretical, but it's right.
Exactly. I mean, it's also memory, but it's also the constraints on the other system, right?
Yeah, of course.
And once we kind of know how to exploit that, I think then we can kind of drive it a little bit faster than, and then I think it may be possible.
I would agree with that. That's my hope. But naively right now, people are just saying, oh, it's a known engineering problem, just copy it. We don't know. Until we understand the physics of life and the physics of chemistry that give you right to life, all this other stuff out there that people talk about, they can facsimile and copy from one place to another, is very, very difficult indeed.
Yeah. So here the interesting thing is that with the automation, with Chemputer, for example, you can kind of mix stuff and you can kind of start building stuff. But then again, how far are you in terms of at least, let's say, reaching at some sort of or if you think of some sort of this self replicating system in a way?
We're in the lab. You mean how close are we to making life?
Yeah.
I don't know how close we are to making life right now. I do know that we have a theory for life, and we have a model, and we have a test, and we have a machine we're building. And I think what we have to do is build a machine and look for evidence of that life coming out. And then once we've done that, go and zoom in and say, right, what is life? Is life a cell? Is life this expanded experiment? How much do I interfere with it? How much will we allow to call life from independently forming, or is requiring on me? Because if I go in the lab and make a life form, then lots of people will argue that that life form came from me, and we're no further forward to understanding where it came from.
Also, like from the astrobiology perspective, right? Like if we want to identify some sort of life form, we need to at least say that, okay, these are the features that I'm looking for. And we can say that, okay, whether this is living or not, right?
Yeah, I mean, I think that's wrong. And the reason why because everyone tries to define life in a different way. So I prefer not to define life because I don't think it's entirely full. I think there's a category error. when you try and define life. But when you ask what is it that life does that non-life doesn't do, that's easy. Life is able to make complex objects that would not form by chance in abundance. And if you can measure those, you can measure aliveness.
And this you can measure it, for example, with assembly theory that you...
yeah, exactly. Assembly theory for life provides the baseline, and you can use assembly theory to help you quantify the transition to evolution.
Yeah, so maybe you can describe a little bit about assembly index, just so people get an idea.
Yeah, so assembly theory. So let's just explain assembly theory. What does assembly theory do? Assembly theory allows you to explain if an object could have emerged in the universe by chance or not. And how do you do that? Well, first of all, you take the object and you say, right, how many identical copies have I got of the object? Right, that's good. You can measure that. Then you say, right, now let's take one of these objects and break it apart and ask myself, how many unique steps are there to recreate this object, right? So if once you get that to around about 15, you can be pretty sure, at least from our calculations on Earth, that this is where the combinatorial explosion for life almost started, and that anything that has an assembly index of 15 or more is definitely alive. So that's kind of cool. And that's kind of how we got started on that.
Yeah, and assembly index?
So the assembly index is like you take the object that you have a large copy number, and you break the object up into parts. And what you do, and this is where the index comes from, if you take your object and you break it into parts, you've got n parts. Now, if you then arrange those n parts in order of recreating the eventual object without any with reuse, you kind of compress in. You assume that the reuse is allowed. Then you count the number of steps, unique steps needed to get to the object, and that gives you the assembly index. And that allows us to then define the assembly equation. And the assembly equation, assembly, so that's the amount, assembly really measures the amount of contingency required to make the object. So where entropy, S, is used to account for the amount of disorder, assembly A tells you how much memory selection the universe has. And the way A is a function of the assembly index for the object and the number of copy numbers of that object. And so that allows us to really explore space properly by counting the number of objects and number of parts it can fall apart into. And for molecules, that's relatively easy. You can use mass spectrometry, NMR, infrared, a whole range of techniques.
Yeah, I mean, that's exciting. And if people can just go and look at the plot that you showed in some of your presentations and also in your paper, where these compounds from the life or living forms, that they have this higher assembly index. It was really exciting to see that.
Yeah, so if you go to the website molecular-assembly.com, it connects you to a fact page about it. There's a calculator, so you can calculate assembly. It connects to the papers. Also, there's an FAQ, and then a connection to just other resources we're putting on there at the moment.
Yeah, and what's the highest assembly index object that you've kind of recorded so far?
It's probably about 45, but that's estimated. But the ones that we've got there analytically are in the about maybe 35.
And what objects are those?
So these are the complex drugs, very small peptides. But we have to be very careful that these fulfill the identity of a molecule and they aren't oligomers or polymers or ensembles of protein, let's say.
Yeah. So other thing is simply that, let's say that now if we, design a mission to go to Mars and collect some material from there. And if we collect some sort of crystal, then another object can be some sort of protein or a virus, or let's say. something like that, some sort of electronics then. So like how we will understand whether it comes from a living form or not? I mean, it's completely hypothetical scenario, but yeah.
Well, there are ways in chemistry to do that. So actually, living systems process different isotopes of carbon differently. And so the more alive you've been, the more, I think, carbon-13 you can have in your bones. In the cell, I think we just got... let me think. I mean, if you were to take... so... You use assembly to measure how alive something is, the amount of memory. You can then use other techniques to secondarily verify that, right? But so you can use kind of carbon dating, looking at the isotopes. But really, what you want to do is look at the number of parts associated with the object. So whether it's a fossil that has molecules in it, or a factory that has drugs in it made by aliens. I think the assembly equation is critical for that. So the A is a function of the exponent of, so e to the AI times the copy number minus 1, and that can be normalized. And that allows you to give to really look at the amount of memory causation put into making that object. And it's not all the same.
And because like how for example we can still characterize it. I mean, let's say that if we in the future, if we can go further outside our solar system and
easy. The nice thing about assembly theory is I made sure it was generalizable without having to know about the molecule in general. So what we did is with mass spec, you can just isolate a single a few hundreds or thousands of a molecule, hit it with energy, see how it fragments, work out the assembly index. And we've done that pretty well. So that will allow you to fly a probe anywhere in the solar system with a mass spec on it and just look for life. The other thing that we're able to use is infrared. And infrared is like the heat you get off your radiators or whatever. And molecules have a very good infrared fingerprint that tells you all about the molecule. And we've done an analysis that actually the assembly index is a function of not just the molecular weight, but the actual complexity of the molecule. So now we could use James Webb and other type telescopes just to get a glimpse of some of these exoplanets and try and look for complex molecules, or molecules at least that could be associated with disequilibria. Then you found aliens.
Yeah, and do we have any components on Earth which gives this kind of IR spectra? And it's like
only the balloons that have been shot down by the American administration.
Yeah.
Yeah, there's a lot of compounds on Earth that have the same characteristic because they're all made from life.
Yeah, so they give this kind of different IR spectra.
Yeah.
So the other thing that I was thinking is, so in general, let's say that if we are able to patch it, still, I mean, of course, there is a lot to explain till we reach at kind of even eukaryotes in a way, because there is still a lot going on at the transition of prokaryote to eukaryotes.
Mm-hmm.
But then the evolution in general, I mean, of course, we attribute it to Luca. But then still it's these kind of transitions, they create a problem, right? So now once we extend the understanding of evolution beyond Luca, does it change afterwards, like once the life emerges, or the underlying principles would be the same all around the...
I'd be tempted to believe that or imagine they would be the same. But you don't know for sure until you do it. But I would imagine it was the same because selection is occurring on a different time scale, right? So the difference between selection that's going on post-Luca versus pre-Luca is that you have cells being propagated, and those cells undergo random mutation. And some of those random mutations are bad. Most of them are very bad and they die. Some of them are good and give you some new advantage. And that's something that we are really interested in understanding in detail.
Yeah, that's great. Okay, so at the end, thank you so much for sharing all the exciting information. I was really interested to talk to you about the assembly theory and, of course, the kind of work that you're doing. So,
well, I think there's three things in assembly theory, I should say. The fundamental theory paper is now done. So there's a version in the archives. There's a new one coming out that I've just finished with Sarah's team and my team. Second one that we've done is we've just finished a practical paper where we can show we use infrared NMR mass spec to detect molecules of complexity. So you've got like a life detector, okay, that we're basically... And the third thing is we're now able to start characterizing what we think alien molecules could look like with different chemistries in general. So you can start to imagine that would go through. And the nice thing about, say, NASA's sending mass spectrometers all over the solar system. So as a mass spectrometer, there are mass spectrometers on Mars. So these mass specs could measure molecules and potentially assembly. And there's a mass spec that did a flyby of Saturn and Enceladus called Cassini, right? And there's Dragonfly with this probe that's going to Titan. And this is literally a nuclear-powered mass spectrometer on a drone that flies around. So I think there's a lot of hope now to get this information and to actually do experiments. And I think that it's super important that we do experiments that don't give us any false positives, because discovery of alien life would be a big deal. It's not just going to be balloons in the upper atmosphere. And so I'm pretty excited that the assembly theory is going to take us a long way. I just think it's funny that I had to invent computation and the Chemputer, the programming language, along the way to actually, go back to these four things: the theory, the model, the measure, the experiment. It's a lot to do, and I'm hoping that we will get a lot of new people, young people, old people, funders alike in the field to help make that work.
Yeah, and it's interesting the kind of progress that you've already made. I mean, I remember I was talking to my colleague and I was explaining her the idea of Chemputer. Once I first got to know, it was like during the lockdown or something. And I was like, yeah, there is some guy and he's trying to do that. And it was really exciting that it can be done, or even from therapeutics perspective, right?
Yeah, we're getting there. I think that's really interesting, but it's still the hardware is getting that to work, and there's you combine electrical engineering problems, chemistry problems, and programming problems, architectures, all in the same, group. You have to get the abstractions right.
Yeah. And that's the best part of it. Once the abstractions are done, it's like hopefully really easy to use it. So so thank you so much for doing this and also kind of progressing the science.
Okay, well, thank you very much, and thanks for doing the podcast. You've got a lot of interesting podcasts out there.
Yeah.